Hello everyone, Assalamu alaikum. This is Dr. Muhammad Rizwan and I am teaching you this course Processor Modeling and Simulation. We are going to start our today's lecture. First, let me share my screen. Okay, so we are going to start our today's lecture. So first see what we have learned in the previous lecture. In the last lecture, what we have learned in the last lecture, we have learned about energy balance. We have learned about energy balance and we have derived a simplified form of energy balance, and I identified the starting point. From that point you can start your energy balance, and after that we have solved two examples. We have solved two examples, and these examples were related with stir tank heating system. And in these example, we derived a dynamic model for temperature, that how temperature changes as a function of time. Okay, and we solved example 5. Okay, that was developing dynamic model for temperature, and here the volume was constant. For constant volume we have derived this dynamic model, and then we solved another example, that was example 6. Here we also derive dynamic model for temperature, that how temperature changes as a function of time, and here uh, for variable volume, for volume is varying. So we have derived these two dynamic models in the last lecture, and in today's lecture we will solve another example, that is example 7. Okay, and this example will be about modeling of a continuous stir tank reactor. Okay, this is modeling of CSTR. So this is a stir tank. I mean, there is a tank and there will be a stirrer, and there will be some reaction inside. So, and also the process will be continuous. So that's why we call it as a continuous stir tank reactor. So CSTR is continuous stir tank reactor. Okay, and so the CSTR has widespread application in industry. So it has many applications in industry. Okay, so here in this example we will consider a simple liquid phase irreversible reaction. So before we go into this modeling part of this example, I will briefly review some theoretical background of continuous stir tank reactor. Okay, so as I said that this is widely used in chemical industry, and for this example we are going to consider a chemical reaction that is a single that's a simple liquid phase irreversible reaction. Okay, so let me write here, consider a liquid phase. So this is irreversible reaction. Okay, and we have the reactant A, this is converted to B. Okay, and we assume that this is a first order reaction. This this first order reaction with respect to component A. Okay, so if we have to write the rate of reaction for this reaction, how we can write? This will be RA equal to minus ACA. This is our equation number 1. So what is RA here in this equation? RA is the rate of reaction of component A. Okay, and this is per unit volume. Okay, and what is K here? K is the reaction rate constant. Reaction rate. Okay, and we have the Ca also. Ca is the molar concentration of component A. This is the molar concentration of component A. Okay, so here in this reaction we have a single phase reaction. The rate constant is typically a strong function of reaction temperature. Okay, so this is, we have the reaction rate constant. Okay, so let me write here for single phase reaction, rate constant uh, is a strong function of reaction temperature. That is T. Okay, so that means the rate of reactions, the reaction uh, rate constant is dependent on temperature. And how we can determine this K? So there is another relationship to determine the reaction rate constant, and that is equal to K is equal to K naught e raised power minus E over RT. This is the Arrhenius relation. Okay, and here in this equation, what is K? K, we know that this is the reaction rate constant, and we have another constant, that is K naught. K naught is actually the frequency factor. K naught is a frequency factor, and this is also a constant, and it varies slightly with temperature. Okay, and then what is E here is the activation energy. E is the activation energy, and R is the gas constant. What is R here? R is the gas and constant. So now we need to look at these two things, that is frequency factor and activation energy. So first revise what is activation energy. I know you are familiar with all these terms, but here I'm just revising these concepts, because these concepts will be used when we are going to develop a dynamic model for this reactor. Okay, so what is activation energy? Okay, activation energy is actually the minimum amount of energy that is required by a reacting molecule to get converted into product. So this is the minimum amount of energy or external energy or extra energy, minimum amount of energy that is required by a reacting molecule or reactant, by a reacting molecule to get converted into product. So that means the reactants required certain energy that we call the activation energy, and they need this energy so that they should be converted into the desired product. And this energy generally, the unit for activation energy is joule per mole or kilojoule per mole or kilocalorie per mole. So these are the units of activation energy. Okay, and here in this equation we have E is the activation energy. Okay, and what is K naught? K naught is also a constant, and that is a frequency factor. And what is frequency factor? Okay, so let's see what is frequency factor. Frequency factor is the rate of molecular collision that occur in chemical reaction. So this is the rate of molecular collision that occur in a reaction. Okay, so we have two equations. Equation one here, that is the for the rate of reaction. This one is equation number one, and then we have another equation, that is equation number two. Okay, that is the for the reaction rate constant, and these two equations are based on theoretical considerations. Okay, so these two equations are based on theoretical consideration, so that's why we call these two equations as a theoretical model, we can say. But uh, if you look at the parameters, okay, so if you look at the parameters, we have the two parameters. One is K naught, that is a frequency factor, and another parameter is E, that is the activation energy. Okay, so equation one and equation two, they are based on theoretical considerations, but we have some model parameters. For example, we have K naught, we have activation energy E. So these two parameters are usually determined by the experimental data, with the help of experimental data or by fitting the experimental data. So that's why we will call model 1 and 2 as semi-empirical. Okay, that was equation 1 and equation 2, they are, sorry, semi-empirical, because we learned the definition of empirical, theoretical, and the semi-empirical model. So in the semi-empirical model, why we call it semi-empirical? Because we know that the actual model is based on theoretical considerations, but some of the model parameters, they are determined with the help of experimental data. So that's why we call equation 1 and equation 2 as semi-empirical models. Okay, so now let's go back to our example that was about continuous state tank reactor. Okay, so let me describe here continuous state tank reactor. So here we have this is actually continuous state tank reactor. So we have a tank here. So this is a tank. Okay, and in tank what we have a stirrer. Okay, and then there will be a reaction. Okay, and it will be a continuous process, so that's why we call it CSTR. Let's say we have here a pure component A that is coming in, and here this is the our outlet of the reactor, and from here we will get mixture of A and, so first let me write the reaction. The reaction is A converted into B. So here I will get the mixture of A and B. So why mixture? Because we know that not all of the A, that is our reactant, will be converted into B. Okay, so here in this mixture there will be some unreacted A along with the B. B is our main product. Okay, and let me label here. So here the inlet volumetric flow rate is Qi, and then we have the concentration of component A. So this is the inlet concentration. Okay, and similarly here, this is the volumetric flow rate, outlet volumetric flow rate, and here this is the concentration of component A at the exit of the reactor. Okay, so this is a simple as CSTR, and we may have the temperature here. Let's say this is T and this is J, but here in this example we will focus on concentration. Okay, so first step, we know that we have to write the objective. Okay, first let me write the objective. Objective is to develop a dynamic model that describes how volume and concentration, that is the concentration of component A in the exit stream, okay, vary as a function of time. So this is our objective. So that means we are going to target two variables. One is the concentration of component A in the exit stream, or the exit concentration of component A, and another one is the volume, okay, volume of the reactor. So this is our objective, and then we have to describe the process. I already described this process. I know we have to label all the symbols or all the notations. So here we have the Qi. Qi is the inlet volumetric flow rate, and we also have the CAI, that is the inlet concentration of component A. Okay, and what else we have? At the exit we have Q. Q is the outlet, okay, or the, sorry, this is the, yes, outlet volumetric flow rate, and we have the CA. C is the exit concentration of component A. Okay, and we also have the volume. This is the volume of reactor, and we have the rho, that is the density. Okay, so these are the symbols that we will use in our dynamic model. Okay, so we have defined the objective, we have described the process. Okay, so we have labeled all the symbols, okay, that we are going to use. And here we have to look that what is our target. Our target is two variables. One is the volume and the other one is concentration. So first we will start with the volume, and for the volume we know that the starting point is overall mass balance. Okay, so I will start with overall mass balance. Okay, and what is the overall mass balance? This is the rate of mass accumulation. Rate of mass accumulation is equal to the rate of mass in minus rate of mass out. Okay, so here this is the mass flow rate, but we will write in terms of volumetric flow rate. And how we can write the volumetric flow rate? So simply we will use this equation, that is m is equal to rho v. I mean, if we multiply the volumetric flow rate with the density, so it will be equal to mass flow rate. And here we can write the accumulation term, that is d rho v over dt is equal to rate of mass in. So this is the rho qi and rho q. Okay, so here one thing I forgot to mention here. So we also have to write the assumptions. So before we start, we also write assumptions and then start developing the model. Okay, what are the assumptions here? So here we have two assumptions. One is uniform mixing, okay, and another one is the density of feed. Feed mean that is the reactant, and product. Density of feed and product are equal and constant. So this is our okay. So let's say this is if this is the density of feed and this is the density of reactant. So yeah, this is the density of reactant, this is the density of product. Okay, so as I said that first we have to define the objective, then we have to describe the process, and we have to label all the symbols, and then we have to state any assumptions. Okay, and after that we have to start our dynamic model. Okay, so here we have assumption that density is constant. Okay, density is constant, so it will become as rho dv over dt is equal to rho qi minus rho q, and we will get the dynamic model for the volume as qi minus q. Okay, let's say this is equation number 1. So this is how the volume changes as a function of times, and this one we learned in many examples. Okay, so now let's go to the component mass balance, because here we have to write the uh, dynamic model for concentration. So for concentration or for composition, what is our starting point? Our starting point is the component mass balance. Okay, and what is the component mass balance? That is the rate of component I accumulation, okay, and it's equal to rate of component I in minus rate of component I out, okay, plus rate of component I, this is produced or generated, okay, and minus rate of component I consumed. Okay, so this is the component mass balance, and I think I already explained that for concentration what we have to keep in mind. For concentration, we know that concentration is more related with number of moles, okay, because number of moles are related in a chemical reaction. So that's why for concentration we will write the molar balance instead of mass balance. Okay, and let me define here the mole. So we will write the molar balance. Okay, so the mole of component A, let's say Na, and how the molar balance is related with concentration. So we can define concentration as moles per liters or moles per volume. Okay, so this is the concentration. Ca is the concentration, and N is the mole, and volume we know that V. Okay, and from here we can get the number of moles for component A, that will be Ca into volume. Okay, so now we have to write the molar balance and the rate of component I accumulation. So accumulation term, we have this one, that is dCA into P divided by dt. Okay, and the rate of component I in, so we have to multiply the composition, inlet composition, or the inlet concentration with the inlet volumetric flow rate. So this is the rate of component I in minus rate of component I out, that is Ca into Q. Then we have to see that the rate of component I consumed or produced in the reaction. So here I will use Ra is the rate of reaction, and we have to multiply it with the volume. Okay, and then we will see that if for the reactant, the Ra is generally represented by the negative sign, and for the product Ra, that is the rate of reaction, is given by positive or the plus sign. Okay, so that we will see at the end of this model. So this is our molar component balance for component I. Okay, so if we look at the unit here, so here this unit is mole per second. Okay, and this concentration, we know that this is mole per liter, and volumetric flow rate, we know that this is liter per second, so liter will be cancelled out, and the unit will be mole per second. So we have here the consistent unit, and similarly this term has the same unit as mole per second. And let's see the unit of this term. So here Ra, that is the rate of reaction, its unit is mole per liter per second, and then volume we have liter. So here we will get the unit of mole per second. So that means we have the molar flow rate, that is mole per liter, mole per second. So we have the same unit or the consistent unit for all of these terms. Okay, so now we can proceed. So let's say this is my equation number 2. So here we have two variables, one is the Ca and another one is the volume. So we need to write with the help of product rule of differentiation, we can write it as V dCA by dt plus Ca dV by dt is equal to CAI QI minus CA Q plus RA into V. Okay, this is, let's say, equation number 3. So now we have two variables. One is the Ca. C is the concentration of component A, exit concentration of component A that we are going to target. And here another variable is the volume, that is dV by dt, and that we already derived. So if you substitute this value, substituting the value of dV by dt from equation, I think that was equation number 1. Okay, and we will put it into equation number 3. Okay, so equation 3 will become V dCA by dt plus Ca, and that was, I think, Qi minus Q is equal to CAI QI minus CAQ plus RA into volume. Okay, so we can simplify this equation. V dCA by dt plus CAQI minus here this term and this term will be cancelled out. Okay, and we can simplify. Okay, so I will keep this term on the left hand side because this is our variable that we are going to target, and this one we can move to the other side. Okay, so I think I made one mistake. Okay, so here this is CAQI and this is CAQ. So what we can cancel here, we can cancel here this term, that is minus CAQ and this one. Okay, and then dCA by dt is equal to CAIQI minus CAQA plus RA into V. Okay, so this will be V dCA by dt is equal to QI, I can take as common. This will be CAI minus CA plus RA into volume. Okay, so now we have to see what is RA. R is the rate of reaction, and that I explained in the start of this lecture, that is rate of reaction. We can write it as minus KCA. So this is the first order reaction with respect to component A. So here we have used the negative sign. So this negative sign is for the reactant, and if we are going to write for the product with respect to product, then we will use the plus sign. Okay, so now our equation 4 will become dCA by dt is equal to QI CAI minus CA. So it will become minus KCA into volume. Okay, so this is equation number 5. So now we can divide volume on both sides. Okay, so if we divide volume on both sides, we will have dCA by dt. Okay, and this will be QI over V into CAI minus CA, and here the volume will be cancelled out and we will have minus K into CA. Okay, so this is the final form of dynamic model, and it represents that how concentration changes with time. So it represents how concentration of component A, how concentration of component A changes with time. More precisely, this is the exit composition. So how exit concentration of component A changes with time. So that is the final form of dynamic model. So here in this example, we have developed two models. One is the that how volume changes as a function of time, and another one how the concentration changes with time. So I will keep this lecture until here.